Right. Good morning, everyone. So today we're going to be talking about convolutional neural networks and computer vision and their applications in aerial imagery. So as I said, we'll start with talking about some computer vision, and then we'll move on to convolutional neural networks, and then looking at their applications specifically in aerial imagery. So let's start with computer vision. So what is it? How do we do it, both with and without neural networks, and then its applications and its difficulties in aerial imagery? So computer vision is basically using a computer to see or detect something in an image. It doesn't necessarily just have to be visual data, especially if using something like a satellite, can often have a much wider range of data. Or for example, your iPhone has some depth information. But in essence, you take this information, you want to see something, you want to do something with that information. So there's a few different types of computer vision. The first type is image recognition, where you're just given some image and you need to say dog, cat, hot dog, not hot dog, etc. Right? Then you have semantic segmentation, which is similar, where but instead of doing the entire image, you need to do it for each pixel. So in this case, all of the sheep in this image have been given, all their pixels have been classified as sheep, and the dog pixels have been classified as dogs. Then you have object detection, which again, you have to detect specific instances of objects, but you also need to be able to differentiate between different occurrences of the same thing. So in this case, with the 3 sheep, each one of those 3 has to be classified separately. And then finally, you have instance segmentation, which will be most of the focus of this talk, where it's kind of a joint between semantic segmentation and object detection, where you need to not only segment out each individual instance of an object that you care about, but you also have to provide a pixel mask for it. So the way that we do this is we do it using something called a convolution. So a convolution is a mathematical operation. For our cases, we're just going to focus on the discrete convolution. But in essence, you have 2 inputs and they do something, and then you get some output that hopefully has some more information than your initial inputs. In this case, we have an input image and a kernel, and convolving those together gives us more information about the input image. So in this case, for an example, our image is of the green values, and our kernels, our kernel is the orange thing where with the red numbers. And what you do is you place your kernel on the image, and you have a center of your kernel. For most cases in computer vision, the center is always the center element of a square kernel. And you place that over some part of your image, and you do the sum of the element-wise products. So our kernel here is 101, 010, 101, see in those red numbers, and you multiply that with the corresponding pixels in the input, and you add that all together. And so if you do that, you get out 4 in your output image. And so you slide this kernel over the whole image, and you get some outputs. In this case, there was no padding, so the output is smaller than the input, but you can pad the outsides with in some way, and then you can retain your dimensionality. But hopefully this output gives you some extra information that you didn't have before. So here, it's a bit hard to see, but on the top left, that was an input image. And what I did is I convolved it with some different kernels, and the outputs are on the bottom there. So on the bottom left, it's a bit hard to see, but I convolved that image with something called the Laplacian kernel, which detects edges in an image. So as if there's an edge, there's going to be a higher valued output after you've convolved. And so you can kind of see that the edges of the peppers are a bit brighter than the insides of the peppers that don't really have any edges. In the middle, I applied what's called an averaging filter, similar to a Gaussian blur, but just a bit easier. And that had the effect of blurring the image. And on the right, I've taken that image and applied both of the filters. And so it's detecting edges, but the edges are a bit softer. And maybe that's a bit more useful if you have a lot of false positives through detecting edges, and you want to blur the image so that only the strongest edges are detected. So what is the point of doing these convolutions? Well, you get some more information out. Let's say you want to detect all the peppers in this image. It might be much easier to detect the peppers if you have their edges rather than just a bunch of different colored peppers who may have some weird lighting that affects your model. So you apply these convolutions and you get some extra information, as I was saying before. So some other types of convolutions you can do, these two filter banks or filters, the ML8 and the Gabor, these are just Gaussian filters with, I'm pretty sure it's just sinusoidal, like it's been changed a bit using a sine wave. And in essence, what you can do with these is you take your input, you apply all of these different convolutions to it, and you build up a feature bank. And that's much better at detecting textures in an input image. So if you took this and put it in something simple, even like logistic regression, and you want to say, is this pixel texture or no texture, then these filters make that your life much easier than just using straight up pixels. So the next thing that we're going to talk about is how you do it with neural networks. So a while ago, computer scientists did what they do with pretty much everything, and they said, can we throw a neural network at it and learn our features rather than having to do this manually? So that's what they did, and it turned out it worked really well. So in essence, what's happening is that we are learning our kernels to make our feature extraction much better for whichever application you want. In this case, this model is called a UNet model. It was developed to perform semantic segmentation on medical imagery. But each of these arrows that you see in this image, all of those are convolutions. Well, apart from the gray ones, they're just copies, but all of these are convolutions. And so this image will go through all of these different convolutions, and you get some output segmentation with classes. And then using that to perform a supervised learning problem where you look at how wrong it is and you back propagate that through all of the kernels, and that helps improve the performance of your model. And if you train it for long enough with enough data, you end up getting a very accurate model. This specific model is something called a fully convolutional network, which means it doesn't have any linear layers or anything like that. There's no hard-coded dimensions. So this network specifically can actually work for arbitrary input and output sizes. This model, mask RCNN, this is a model that was developed for instance segmentation. So with instance segmentation, you need a little bit of an extra step where you not only need to take the pixels, you need to take the bounding boxes. So that first big box, region of interest, it does some feature extraction and develops regions of interest, which then gets passed into a convolutional neural network to perform the instance segmentation on each of these regions of interest and predicting pixel masks and bounding boxes and classifying objects. So now that we know vaguely how computer vision is performed, let's talk about how its applications in aerial imagery. So aerial imagery is a bit unique when compared to natural scenery. So the image on your right is something that's like a natural scene, something you've taken maybe a photo on your phone or something like that. And often it's from, you're pretty close to your objects. Is not really going to be a huge change in scale within a single image. And it's unlikely that you're going to have a very high density image unless you have some very specific applications. Whereas in aerial imagery, you can see the image on the left. This is a photo from Google Earth, and all of the objects of interest have been colored in here with different colors. So this is a picture of an airport, and you can see that we've got a bunch of airplanes. Those small dots up at the top are all cars, and then there's a circle thing, which may be a water tank or something like that. And you can see here that compared to the natural scenery, we have a bit of a bigger scale change, and you have a very high density of objects, especially, for example, with the cars. You have a lot of cars that you want to be able to detect all of them. And you somehow have to deal with the super high density, large change in scale, and you also have many more instances of objects appearing in a single image. Unless you're taking a very small satellite image, you're likely going to have many more instances of your objects that you care about in a single image. So with aerial imagery, these are things that have to be accounted for when you are designing your models, testing and training your models. So now we know why it's difficult. Let's talk about why we might want to do it. So these are just some applications. There's many more that I haven't spoken about here, but for example, if you are Google and you want to go map some remote area, but you don't want to pay someone to drive out there, and it takes a week, and it does all the, it's not very easy. If you have satellite imagery of the area, you can just detect all the roads and pass that to Google Maps, and you can use that to build maps for you without having to send a person down all of the roads. You do a similar thing with building detection. Maybe you're looking at population density. If you're detecting cars with car density, you can use that for traffic predictions. Maybe you have a census and you want to see if there's any statistical anomalies saying that, oh, this area says they have only 5 people, but they've got 100 buildings, stuff like that. And this is stuff that you won't necessarily want to do manually. So you'd much rather take some satellite imagery, or maybe you're taking photos with drones and you do this automatically. If you want to track animals, let's say you're in the Kruger National Park and you want to track a herd as it's traveling through the park, or you want to track its population and you have satellite imagery of the park, you could maybe detect the herd, count the number of individual occurrences of animals and use that for herd tracking or population tracking. Cool. So spoke about computer vision and aerial imagery, and yeah, that's it. Thank you very much.